Hey, I'm Todd Mostak. I'm founder and CEO of MapD Technologies. MapD, we build a GPU-powered database and visual analytics platform. Actually came out of my research at MIT in the database group at MIT CSAIL. I'm going to tell you a little bit today about the ins and outs of a GPU database, doing visual analytics at scale, and then I'll conclude with a brief demo. So everyone's seen charts like this, right, where we're seeing this kind of exponential increase in data. I think IDC says that actually we're looking at 50% year over year increase in different sources of data. Some of that's coming from traditional enterprise sources, but a lot of it is from kind of new sources like social media, IoT or sensor data coming off of smartphones, telemetry data from cars, industrial automation systems, engines on airplanes produced terabytes of data per minute. So we're faced with this deluge of data, and the problem no longer is storage. So storage is actually getting cheaper at an even faster rate than data is getting bigger. I think by 2020, it's estimated that you'll be able to put a terabyte on disk for about $8. And Hadoop has basically become, the data lake of our time has become the tape of our time. So it's easy to kind of throw data sets onto disk, but then what happens? So one of the big issues is that if you want to analyze this data, if you want to do any kind of real-time analytics, I'm not talking about batch workloads that run overnight, but if you want to slice and dice this data interactively to get insight, basically you're faced with CPUs that since 2004 aren't getting much faster. So 15 years ago, basically engineers hit a clock speed wall where they realized that about 4 gigahertz to increase the clock speed of these CPUs required kind of an exponential trade-off, both in terms of power consumption and heat generation. And so what they did is they started to use, Moore's law was still continuing apace, and they were still getting more transistors every year. And basically they started putting these to making smarter cores, having bigger caches, and eventually started putting them towards multiple core CPUs. But basically the idea was that it would make dumb code or unoptimized code run faster, but it wasn't necessarily helping optimized code run faster. This is where GPUs come in. So GPUs, obviously they're video cards originally designed to accelerate rendering graphics to a screen when you're playing something like Doom or Quake, have basically evolved into these general purpose computational engines, very popular across the HPC space, of course increasingly in machine learning. You probably hear every day about something in deep learning being driven by GPUs, and then increasingly in data analytics, and that's where we are. And one of the nice things about GPUs is that the model is simple. Basically, you get these more transistors. The model is inherently parallel. You add more cores, you get more speed. And so every year we can see this kind of 30 to 50% improvement, both in terms of flops, the computational throughput, but probably even more importantly for analytics, you see it in memory bandwidth. So GPUs have been early adopters of kind of the fastest memory technologies like GDDR5 and increasingly high bandwidth memory, where you can have nearly a terabyte a second per card. Across a single server, you could have 5-6 terabytes of bandwidth a second, which is significantly orders of magnitude faster than you would have on CPU, which means you can literally scan that much data in a second. And so again, it's the cores and the fast memory. I don't want to equate CPU cores to GPU cores. They're not equal, and it's a bit of a marking thing. But you get the idea that you have a lot more parallelism on GPUs as well as this higher memory bandwidth. So that's where MapD comes in. So we have a kind of two-part product. MapD Core is basically a in-memory column store relational SQL database that leverages these GPUs. It was actually built from the ground up to take advantage of the parallelism and fast memory of these GPUs to basically deliver 100+x speedups on SQL queries. And then because the use case when you have so much speed is so often kind of slice and dice visual analytics, wanting to explore large data sets at scale, drill down, find correlations, we actually built our own front end called MapD Immerse, which leverages not only the speed of our backend, but the ability of the backend GPUs to actually render data. So we can use the GPUs also for what they were originally designed for, which is to actually render graphics. And I'll give you a demo of that in a minute. So lots of proof points. We've been independently benchmarked by a noted database blogger against a variety of CPU-based systems, including BigQuery, large Redshift cluster. Even on a single node, he found us to be anywhere from 74 to 3,500x faster than these systems. We've done some other benchmarks where we've scaled to 40 billion rows and done some benchmarks with Google and AWS. So if we were just to naively use these GPUs without consideration of where we did the compute or where we put the data, we wouldn't be seeing the speedups that we're actually getting. So one of the hallmarks of MapD is basically its ability to actually cache the hot data that you're actually querying on the GPU RAM itself. So when I started my first prototype of MapD probably 4 years ago, there wasn't much GPU RAM out there. You might get 6 gigabytes per card. You may have 4 cards per server. 24 gigabytes didn't get you very far. Fast forward to today, and you can have 32 gigabytes per card. You can have 10 cards per server. Some specialized servers, you can actually have 16 cards. So you're talking about a significant amount of VRAM that's very, very fast, right? And so because we're a column store, we don't need to query all the columns typically. Because we horizontally partition, we don't need to necessarily touch all the partitions. And finally, because column store architectures are very amenable to high levels of compression, we can basically fit a lot of data in this GPU RAM. And if the data is there, because we have all this memory bandwidth and parallelism, the queries are just going to be lightning fast. I'm talking about milliseconds over multi-billion row data sets. If it can't fit there, we can actually spill into CPU RAM. So CPU RAM is, of course, much bigger typically, could be up to terabytes per node, but also much slower. And you can think of that as sort of our L2 cache if the GPU RAM is our L1 cache. And then finally, what doesn't fit there, we can spill into SSD or NVRAM. And we're also very fast at pulling off a disk, but of course, it's not going to match the speeds of what you see up top. And then finally, we can pull from kind of your store of record, which may be your data lake, like Hadoop or another data warehouse. A few other things we do that differentiate MapD. One is we compile our queries on the fly. Since we're so built for speed, it wouldn't work if we were just to interpret our queries like a normal database does. So we've put significant effort to actually compiling GPU code on the fly using something called LLVM, which is an Apple-backed open source compiler infrastructure. And so that gets us the speed of handwritten functions. And not only that, because LLVM is modular, we can generate CPU code, we can generate GPU code. We can actually run on both at the same time and take advantage of both architectures. So that's a nice advantage of MapD. Two, I spoke about this briefly, back-end rendering. Imagine the use case where you're trying to use Tableau on something like Vertica or some in-memory engine, and you're trying to visualize big geodata at scale. For example, like you have billions of tweets or call records or car telemetry data, and you actually want to see that on a map. The issue is that maybe the back-end could query it. It's going to be slow. It's a CPU system. But even if it did, how do you get all that data to the front end to render from server to client? It's going to be multiple gigabytes of data. It's going to take you all day to actually transfer that data. So MapD does something different. We actually run the SQL queries on the GPUs, and without even needing to copy it to the CPUs or to the client, we can actually render it right in situ, in place on the GPUs. And it's very fast. We generate a compressed PNG that instead of tens of gigabytes is probably 100 kilobytes. Send it to the front end, and it's completely interactive to explore multi-billion row data sets visually, whether in a scatter plot, on a point map, on a choropleth, at scale. And then finally, because we're using the brute force of these GPUs, it allows us to avoid a lot of the kind of indexing, pre-aggregation, cubing strategies that other data warehouses use. The advantage of that is that means we can push data into the system very fast. So MapD is a very good architecture for kind of continuous data integration. We're actually streaming in data in real time, so you get the stream as well as the near historical data. And I'll demo that briefly on some Twitter data. Cool. So how many minutes? 5? Okay, let me hurry. That's where we are in the ecosystem. Sitting on top, usually, of other systems of records, powering our own friend. You can also power something like Tableau. We can bring in streaming data. Okay. Since I only have 5 minutes, I want to make sure I get to a demo. So this is 1.2 billion records. Every taxi ride in New York City from 2009 to 2016, nothing here is pre-aggregated. So you can see here we're actually rendering this. This is an example of GPU rendering. You wouldn't want to pull 1.2 billion records from server to client. Say I wanted to zoom in here to JFK, and you saw how interactive that was, right? We basically, all these charts hit queries, sent queries to the back end that came back in maybe tens of milliseconds. Here we're coloring by the pickup borough, looking at taxi drop-offs. Everything in our immersed interface is interactive, right? So I can just brush, and we're just hammering our back end with these queries, but it's fast enough to keep up, right? Similarly, I could brush over pickup time, and one of the interesting things is that you're going to see kind of basically this area drop off. That was actually when they knocked down the Pan Am terminal at the end of 2013. So our clients really like this, right? Like if you have big data sets, log data, geodata, you can actually explore this at scale. So whether it's Verizon or Facebook, people are using this to basically do interactive exploration of their data. We've also made it very easy to kind of add different charts. So say I wanted to look at a new dimension like payment type, I can just make a table, a row chart, and then immediately it's an interface. I can see credit usage is going up over time. People are paying for their taxi rides with cash less and less. One quick other demo. This is a smaller data set, but I think this is running on a few GPUs. Relatively small for us. This is most recent 400 million geocoded tweets in the world, and this is streaming up to the, basically up to the second here. So I can zoom in the US. Here we're looking at whether the tweets are coming from iOS or Android. And I can look at these various spikes. And actually, if I zoomed in on them, I would see that the first one was the debate. You can see these are the top hashtags, which we're kind of aggregating in real time. This one is another debate. This one is actually the World Series. So we could drill down there, and we could actually look at the raw tweets. You could go into Chicago. And then the last one is, as you might expect, is when Trump won the election, which people got quite excited about. So the cool thing here is because this is streaming and because we're not aggregating it all, I can actually drill down as much as I want. I don't have to rely on some pre-aggregated cubes. So why don't I go into San Francisco? Oops. So here we can see all the tweets coming from the city. And say I wanted to do, so a few tweets here. Oops. So a few tweets here, and then you can see right before my talk I actually tweeted, and it popped up on the map. So kind of gives you an example of the real-time capabilities of the system and what having GPUs allows you to do. Am I about out? Yeah. If you want to go to our website, basically we have all these demos online. This is another fun one. This is every political donation from 2000 to the present. So you can explore all kinds of trends like Republican versus Democrat, who gave to Barack Obama, things like this. And yeah, I just want to conclude by saying that, we feel that we're at an inflection point in compute. CPUs aren't able to keep up with the data that we're seeing, the ever-increasing amounts of data that are coming in. If you move to GPUs, you have the fastest possible software, but then you need the fastest software. You have the fastest hardware, and then you need the fastest software, and that's where MapD comes in. All our clients need speed at scale. Increasingly, doing batch workloads is not enough. People need real-time insight on their data, and we excel at that. And then we strongly believe in integrated analytics. It's not enough just to be the database. If you can actually combine the stack, you can do things like we're doing, where you're not only doing the query acceleration, but also the rendering acceleration. And increasingly in the future, we're looking to push kind of machine learning into the database as well. That's something GPUs do very well. Great, thank you.